Yo, 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 yo. Today I'm going to solve problem 907. Sum of subarray. Sum of subarray minimums. Um, this problem is classified as a Leetcode medium, but in my personal opinion, and it seems to be the opinion of most individuals who solve this problem, this is likely a hard. Um, this is just an example among a multitude of examples where Leetcode incorrectly classifies the problem. Now, there's definitely some subjectivity to a problem's classification, right? But this is definitely a difficult problem. It took me a long time to figure out kind of the optimal solution and even just to gain intuition once I figured out the optimal solution, because there was a lot of just brute forcing and trying different things to try to make this work. In many ways, it's a beautiful problem because the intuition required is so unintuitive, right? But once you see it, it can be very helpful, and the pattern is very unique in its own. But that's kind of besides the point. Let's go ahead and get right into the problem. Done rambling about how difficult this problem is. Okay, so you're given an array of integers R. Find the sum of min b, where b ranges over every subarray of array. Since the answer may be large, return the answer modulo 10 to the 9 plus 7. So very simple problem description, right? I mean, it's like 2 sentences. So how could it be hard, right? It's a medium problem. The problem description, the problem statement is very short. What's the issue? Well, let's just go ahead and get right into it. So if this doesn't make sense, essentially what you're doing is you're looking at all possible subarrays, right? So there's continuous parts of an array, all possible subarrays. And then what is the minimum element in that subarray? Take the minimum element from each subarray, add them up together, and return it. That's essentially what we're doing. So if we look at our first example of array equals 3, 1, 2, and 4. Let's first just exhaust all possible subarrays. So, we have the subarray that ends in 3. We have the subarray that ends in 1, so there's 2 of those. We have the subarray that ends in 2. We have sorry. You might be asking me, why am I writing it like this? And it'll make sense later. Let's just draw it like this for now. 3, 1, 2, 3, 1, 2. What am I doing? The subarrays that end in 1. I'm very sorry, guys. I don't know what is going on with me right now. Having a little bit of a brain malfunction. Okay. Subarrays that end in 1. Okay, the subarrays that end in 2. So we have 1, 2, and we have 2 here all alone. 3, 1, 2, and then we have the subarrays that end in 4. Finally. Okay, and 1, 2, 4, and then 2, 4, and then 4 all alone. So is this all the possible subarrays? Sorry, so we have all the length 1 here. So 3, 1, 2, 4, 3, 1, 2, 4, 3, 1, 3, 1, 1, 2, 1, 2, 2, 4, 2, 4, 3, 1, 2, 1, 2, 4, 3, 1, 2, 1, 2, 4, 3, 1, 2, 4, 3, 1, 2, 4. Okay, so they're all here, right? Now you'll notice that these are the way I have it set up here, right? Subarray ending in 3 is here. Subarray ending in 1, they're here. Subarrays ending in 2 are here, and the subarrays ending in 4 are here. That observation might be important later, depending on how I approach explaining this. I haven't even really totally figured that out yet. But so if we go through this, right, for 3, what's the minimum element for 3? Well, that's just 3, right, obviously. What's the minimum element for anything ending in 1? Well, that's the minimum of the whole system. So this is going to give us 1. This is going to give us 1. The minimum of this subarray is 1, so we add 1. The minimum of this subarray is 1, so we add 1. For the minimum of this subarray is 2, so we add 2. The minimum of this one is 1. The minimum of this one is 1. The minimum of this one is 2. The minimum of this one is 4. And then if we add all that up, 3 plus 1 plus 1, that's 5, 6, 7, 9, 10, 11, 13, 17, and output 17. Okay, so that essentially makes sense. then the easiest solution to this problem, right, the brute force solution would be n cubed. So you could literally look at all subarrays, right? So you could have like a left pointer and a right pointer, and you'd have this sliding window. So you could look at all possible subarrays. So that would give you n squared things you'd have to look at, right? And then you'd have to look at all the elements in each of the subarrays. So literally create each subarray and then do what we've just done and check each element and find the minimum. When you find the minimum, you add that to some running sum, and at the end, you return that running sum. But that's an n cubed solution. And if you look at these constraints, right, this is 10 to the 4, right? Your array could be 10 to the 4, so n cubed. It's going to be 10 to the 4 times 10 to the 4 times 10 to the 4. That's 10 to the 12. That's going to be far too inefficient. So we got to do something a little bit better than that. I guess a quicker solution would be to look at each subarray that corresponds to adding an element, right? So when I guess the first thing we could do to make this faster is, I guess we could think about each subarray that gets created when you add an element to some running instance of things. What I basically mean by that is, like, if we're looking at 3, 1, 2, and 4, right? Because that's our example here. When we add a 3, there's only one subarray that's created, right? And that's going to give us a total of, I use red here, right? So that's going to give us plus 3 in terms of our total running sum. When I add another element, what you'll notice is when I add 1, there's 2 subarrays that are now created, right? Because there's a subarray associated with 1 by itself. That's this one here. Right, so if I did that with color, there's 1 by itself, which is this one here. And there's also 3, 1, which is this one here. Right, so if I have n elements and I add an nth plus 1 element, there's n plus 1 subarrays that end in that element, right? So basically what I'm saying is, if I have a running sum of characters like this, right? And then I add an additional number like 2, right? Well, there's going to now be 1, 2, 3, 4, 5, 6, 7, 8 subarrays ending in 2, right? Because there's this one and this one, there's it by itself, and this one and this one and this one and this one and this one, right? When I create 3, 1, 2, 4 and I look at 2, right? There's going to be 2 by itself, 1 then 2, 3 then 1 then 2, right? So there's kind of this running sum idea that I can look at, right? So when I do this problem and I add 1, right, I can consider 1 by itself as a subarray, and that's going to give me plus 1 points when I just consider 1. And then when I consider 1 and 3, I'm going to get another 1 because 1 is the minimum subarray of 1 and 3, right? Now, notice that any subsequent element that comes after this, okay. We can also think about this system like, what if we thought about this as the minimum subarray starting at some position and ending at some position? So what would be the minimum value, right? Because the minimum value in this system by itself is 1, ending in 1 is 1, and including 3 is also 1. Does that make sense? Because the subarray 3, 1, what's the minimum value? It's 1, right? Because this like falls apart and becomes 1. And anything else that includes 3 also becomes the minimum of at least 1, right? The largest thing the minimum can be now, if it includes 3 and 1, is 1. So you can kind of think about replacing this with just the 1. Right, like this 3, 1, the 3 is unimportant, right? Because 1 is less than it. So since 1 is less than it, 1 will be chosen as the minimum value over 3. So we don't need the information about 3 anymore, right? Because any subarray that includes 3 from this point forward, since we've already considered 1, any subarray we consider, right, since we're going in order, we're going to consider a value that comes after 1. So in order for that value to utilize 3, it has to use 1, right? If I have 3 and then I have 1 any value that comes after, if it wants to use the 3 as a part of its subarray, it has to also use 1. So the idea is that the fact that this is a 3 is irrelevant because there's a lesser value to the right. So to kind of articulate that idea, we'll replace a number if it's less than us to our left with 1. And what that will also mean is that this subarray will represent the minimum value starting from this position going to the newest values position. So far, I already messed up what we have, but we had +3 here, and then we had +1 and +1, since we had 2 things we can consider. And then the next value we're going to consider is, well, 2. Okay. When we look at 2 by itself, we get +2, right? Because that's the minimum value of the array by itself. And then if we attach, if 2 is the last element of something of length 2, well, 1 is already less than 2, right? So we don't need to change any value. The minimum value in this subarray is 1. So we add 1 here. And the minimum value in this subarray, right, is also 1, right? Because the 2 doesn't change anything. It doesn't get moved over, and 1 is less. So we add another 1. Okay. And then the next value we're adding now, the last value is 4. Same idea, right? We don't move it over, right? Because 4 alone, we get +4. When we look at 2 and 4, 2 is the smallest, right? 2 is the smallest thing in this subarray. So we get +2, and then +1, and then +1. Okay. So what does that equal in the end? Well, we got 1 + 2 is 3, 4, 5, 7, 10, 11, +6, 17. So we got 17 again, doing it this way. This is an interesting problem. Now, this is shorten the solution to n squared, right? Because we just look at each element and we look at everything that comes before it. And we say, okay, everything that comes before it, every element that comes before this element is a subarray ending at this element, right? So if I look at this element, then there's a subarray 2, 4. If I look at this element, there's a subarray 1, 2, 4. If I look at this element, there's a subarray 3, 1, 2, 4. And I can just account for what the minimum value is within that subarray, starting at this position, ending at this position, save that information in this array, and I can always make an assessment about what this system looks like, right? So there's a lot of information encapsulated in what I've just done, right? Because I got like this growing system, and using this growing system, there's an invariant that every time I add an element, I'm saying I'm going to count each subarray, the minimum value of each subarray when I add that element by traversing the array in reverse from the element that I've added to get the minimum value from the subarray. So this is there's a lot of convoluted information encapsulated in this simple idea. And this gives us an n squared algorithm, but guess what? It's still not efficient enough. Okay, so let's look at another example, and then we'll see if we can kind of use that to even further make this problem more efficient. Okay, so we got it down from n cubed to n squared, right? But n squared would be 10 to the 8, so still not 9 times 10 to the 8, which is basically 10 times 10 to the 8, which is 10 to the 9. So that's still too large. So let's look at a different example. I keep saying that and then not doing it. So let's look at 3, 5, 4, 1. So simpler example. So when we look at 3, it's 3 alone. There's nothing to compare it to. We look at 5. Well, 5 alone will give you +5. And then 3 is less than it, so 3 will take over in the next iteration. All right. And then what happens when we add 4? Well, okay, 4 alone, we get +4. When we do 5 and 4, well, what's the minimum value in a subarray starting at 5 and ending in 4? Well, this value then becomes 4, right? And then we get +4. And then what about when we add our final value of 1. Well, 1 alone, we're going to get plus 1. 1 and 4, what's the minimum there? Well, the minimum is 1. Right, so that means that this value becomes a 1. Right, and we're traveling this 1 over. So the minimum is 1 now. And then we compare these two and we say, okay, what's the minimum, 1 or 4? But that means we get plus 1 here, right? Sorry to forget to the steps. And I compare it to the previous element. I say, okay, what's the minimum here? The minimum is 1. So I'm kind of propagating over the minimum value as far as I can get it. That way I have the invariant that inside of my system, when the last element is this one here, the minimum value starting from 4, the subarray starting from 4, ending in this is 1. The minimum value starting from 5, ending in this is 1. And then finally, we play the same game again. I'll remove this. We compare these. This becomes a 1. And this becomes a plus 1 again. Okay. So, and then we just add all these up and then we get the solution. Okay, so you'll notice this idea of things propagating over to the left because you want to find the stack where the minimum value of an array starting at a position, the subarray starting position, ending at a position, right? So for all of them, they're all 1, right? Because they all end at 1, and 1's the minimum value in this whole system. So they're all going to have the minimum value of 1, which is why you see this here. Okay, so what's the first thing we can fix with this system? Well, you know, I don't really need to, like, save additional information, right? When we looked at this here, all right, it goes from 3 to 5, right? And then when we add 4, what if instead of changing this to a 4, we just remove this element, we shift this one over, and then we just keep a counter to say that there's 2 of these in a row. A count. And that there's 1 of these in a row. Right? So then when I add the 1, instead of having to look at all 4s, well, I know if I'm replacing the 4, I'm going to replace all the 4s, right? Because it's going to be the same thing, right? So instead of saying, okay, I'm going to replace a 4, then a 4, I know I'm going to replace 2 4s, and I have 1 1 currently. So instead of having to go through each of the 4s, just the fact that there is a 4 that I'm going to erase, right? I could say, okay, what would that mean in terms of what I add? So if there's 2 4s before me, right? So when I have 1 and 1 here, you know, of course, I do the same thing I always do. I add a 1, right? Let's do it in red because that's what I was doing before. So I add a 1. Now, there's 2 4s that come before this one that I'm adding right now, right? There's 2 4s that come before this 1 1 that I'm adding right now. I'm less than it, so I'm going to end up replacing both of those 4s, right? Because what this basically is articulating, right, is that there's a 3, 2 4s, and a 1, right? But this one's going to end up replacing both of these 4s. So that's equivalent to saying, okay, well, that means there's going to be no more 4s, but there's now going to be 3 1s, right? Because I'm going to end up replacing both of these 4s with 1s. And how many do I end up adding to my solution? Well, if there was 2 4s, that means there were 2 cases where 1 is now going to be the minimum because it's going to be less than those 2 4 situations, right? So these 2 4s meet these 2 situations. So instead of adding 1, I'm going to add 1 times the number of cases that I got, which equals, you know, plus 2. Okay? And then I see 1 and 3. Well, that means I'm going to replace 1 3 with a 1, right? Because 1 is less than 3. So this becomes 1 4, right? And then I added an additional 1, so times plus 1 times 1. Okay, so now I just have one element in this stack. Instead of having traversed the whole system, I can remove values and just keep account of how many times they occurred. That way I don't have to traverse through the whole system again. Okay. So how do I explain this kind of more simply? Let's do the 3, 1, 2, 4 problem again using this new approach. So we have 3, 1, 2, 4, right? 3, 1, 2, 4. Sorry that it's there. It's unfortunate. So I add 3. And I say, okay, I add 3. That's going to give me, and 3 is going to occur once. What am I doing? 3 occurs once, and that's going to give me 3 times 1 points. So I'm going to get 3 times 1 points from doing this. Okay? And then the next element I add is 4 with occurrence of once, right? Because every time you add something and it's occurred once in that current position. And then 4 is not less than 3, so I don't absorb anything to my left. I don't replace it, and replacing it means I just eliminate that value and then add an additional number tier depending on how many values that thing had that existed. Ugh, confusing what I'm saying right now. 3, 4, 1, 2, right? Oh. 3, 1, 2, 4. So instead, what if I did the right thing? So if the next value I added was 1, then imagine that, right? It starts off with occurrence 1. That means that this system gets 1 times 1, a plus 1 times 1 to it. And then since 1 is less than 3, I'm going to replace this 3 with a 1. But instead of doing what we did before, which was creating additional space we didn't need to use, and it could create additional computations in the future, we could just say, oh, well, that's the same thing as just taking 1 and saying it occurred twice. And since now 1 occurred twice, that means that there's an additional case where we have plus 1 times 1. All right. And then when I add in 2, so I look at 2. 2's occurred how many times so far? Just once. So that means I'm going to get an additional 2 times 1 occurrences. And then I compare 2 to the previous element. And I say, well, 2 is greater than this, but this thing occurs twice. So there's going to be 2 additional cases, 1 and 1, where 1 comes before this 2 and it's less than. So I'm going to get an additional case where there's 1 and it occurs twice. And then I do the same thing with 4. 4 occurs once. I'll add 4 as itself. I'll add 4 and 2 occurs, and then I'll add 1 twice because there's 2 cases where 1 occurs twice. Okay, so this is an N algorithm now, right? Because I add an element once and I only remove it once, right? Because if I remove it, I just increase the count of an element, but I never have to look at it again. So I always add an element at most one time, and I always remove an element at most one time. So that's an N algorithm. The problem is that these sums are not N, right? Because every time I find a computation, I have to look at all the previous elements to make a computation about, what belongs, right? Like, even though 4 is not less than 2, I have to look at 2 and 1 to figure out what I'm supposed to add to the system. So I guess the last observation that I'll make is, let's do 2, 3, 4, and 1. So let's look at this example and look at what the sums look like. So first we add 2. And it has count 1. And you'll notice that our sum is 2 times 1. Okay? And then we add 3 with count 1. Now, what is our sum going to be now? Well, it's going to be plus, for this new solution, it's going to be, so this is for the first case, right? 2 times 1. Now it's 2 times 1 plus 3 times 1. And then when we add 4 with occurrence once, what's the new sum now? the new sum is, let's make these square brackets so you see what I'm saying here. Well, there's going to be the case where it's 4 alone, 3 and 4, 2 and 4. So that's 2 times 1 plus 3 times 1 plus 4 times 1. Right? Because this is the case where 2 is the first element and 4 is the last element. This is the case where 3 is the first element and 4 is the last element. And this is the subarray where 4 is the first element and 4 is the last element. Right? So these are each of the subarrays. I'm adding them together. And then the last case is 1. Now, when we add 1, that's when it gets fun. When you add 1, it gets fun, right? Because 1's going to look at this and say, okay, I'm going to replace this 4 with a 1, which will make this 2. Right? And then, I'm going to replace this 3 with a 1, which will make this, there's going to be 3 1s in a row. And I'm going to replace this 2 with a 1, which will make 4 1s in a row. And you'll notice that that corresponds to is plus 1 times 1, 1 times 4, right? 1 times 4 occurrences. So you'll notice here is that we kind of have a running sum, right? We looked at 2, and then we added 2 to our solution. And then we looked at 3, and then we added 2 plus 3 to our solution. And then we looked at 4, and we added 2 plus 3 plus 4 to our solution. The only thing that changes when we added 1, right? When we looked at 1, since we replaced elements, we had to take our previous solution, which was 2 plus 3 plus 4 plus 1. But then we had to subtract out 4 and 3 and 2 because we removed those from the system because those are no longer the minimums, right? Because now 1 is the minimum. That's why it's getting propagated left. So since 1 is the minimum and it's getting propagated left, it becomes the minimum value. So this sum is no longer valid. So we have to remove 2. We have to remove 3. We have to remove 4. And then we add in 1 because, you know, when you had 2, 3, 4, 1, when 1 was alone, it was its own minimum, which gives you this value. When it was 4 and 1, well, 4 used to be a minimum, but now that minimum is 1. That's why you minus 4. So you get an additional 1. Here you get an additional 1. And here you get an additional 1. So as long as you keep a running sum of what you've seen, and when you move a value over to the left, right? So when something's a minimum and it's less than the values to its left, you subtract out those previous values from the array. And then when you gain new minimum values, you add those to the array. And then as long as you keep that running sum, you keep adding it to your solution at every iteration. That way you have a constant operations that you have to do when you solve this problem. Okay, so that's the best I can explain. I've been rambling far too long. It's just a very hard problem. So let's use a stack to represent adding the strings and then removing the strings, right? Because we add an element, the strings, why did I say strings? You add an integer, you do some computation, and then you remove the integer, right? You add an integer, you add some, and then if it's less than the things before it, you remove. So we'll say stack equals nothing. We'll have a solution, which will just hold the sum of everything, right? Because we keep adding these sums of minimums. So that's what we'll end up returning at the end. So we're going to return the solution. And I don't want to forget that we're supposed to mod it by 10 to the 9 plus 7. Okay? And then we'll have this running sum, right? Which was these values up here, right? This running sum that we're going to use to ensure that we have the element equals 0. So we're going to look at each num in the array, right? Now each num by itself is going to get added to the sum every time, right? Like when you have a 2, the 2 gets added. When you have a 3, the 3 gets added. When you have a 4, the 4 gets added, right? Because every element is its own single subarray. So we'll end up adding that to the sum. So we'll say sum plus equals the num. And at the end, what we're going to do is we're going to take the running sum, because the running sum will be all the minimums that end at that index. So we'll have the sol plus equal the sum. Now, before we add an element, what we'll do is, you know, like here, the element got added and we started removing the things that came before it to get here, right? So we'll say if there's a stack, right, and the number that we're adding is less than the value at the back of the stack, so the last value in the stack, we're going to say, okay, that value that's in the stack, so stack num, and well, the number of times that this value's occurred so far, the first number we're adding is once, right? We'll say stack num and stack count. We'll call it s num, I guess. S num and s count. It should be the other way around. So I haven't really revealed the structure of the stack yet. We'll pop the vast value from the stack because that's what we're removing. And then the number of times that that value occurred, and that value is going to get removed from the minimums, right? Because since that value's been removed, that means that the subarray ending at the current value we're looking at, if we're removing the value, that means that it's less than the last value in our subarray. So that means that that value is not the minimum, so we don't want to add that to our solution. We want to add in, right? We want to substitute in our minimum value, right? If my sum was the weight of this bottle, okay, and then I looked at a current value, which is this new bottle, which weighs less, right? This bottle has weight, which is going to be my total sum. But since I want the minimum value's weight in my subarray, when I add a new value, I basically want to substitute this value out of the sum and add the replacement, which is less than it. So I'm basically just substituting, right? Because I want to add up the minimum value in the subarray. If I get to this point, that means that the value at num, which is the last value in the subarray I'm looking at, is less than this value in the stack. So that means that the value I'm adding, num, is minimum, right? So we don't want to add in the value at stack -1. We want to add in num as the minimum value. So what we'll do is we'll say, well, now sum equals sum, what the sum was before. We're gonna substitute them. So we're gonna minus out the number times the number of times it occurred, and then we're gonna add in our current number times the number of times it occurred. So we're just directly substituting, right? Because if there's 4, 4, 4, 4, 4, if there's 4, 4, 4, and then a 1, we're gonna replace all three of those 4s with a 1, right? So if there was 3 4s, we're going to remove those 3 4s from our total weight and then add in the 1 with 4 because it's going to replace all 3 of those 4s. And that means that this number, right, if 1 replaced 3 4s, now 1 is of weight 4, right? Because there was 1 1, it replaced 3 4s, so now there's 4 1s. So then we'll say, okay, now the count of this number plus equal the count of the number on the stack. And at the end, what we have to do is we have to put this element onto the stack. So we say stack, we're just going to push, which is, we're using a list, so we'll append. And then we'll append the count of the number of times that we've seen this number and the number itself. Okay, and then let's do the test case here so you can see how this works. So before we do this, we'll print the stack. So we'll print the num, and then we'll print the stack. And then we'll print the sum, I guess. So after I add 3, right? After I add 3, it's just 3 on the stack, and there's just one case of 3, right? The count of 3, and the total sum is 3, right? When I add 1, I end up replacing that 3 with 1, so I absorb it. So now there's 2 1s in a row. So 2 1s in a row, and the number of times that occurred is twice. I then add 2, but now there's 2 is not going to replace 1, and 2's only occurred once, so I add the 2 into the system, but 1 is still the minimum, so the sum is the same, so it's just 2 plus 2 to give you 4. And then when I add 4, right, the system's the same because 4 doesn't replace anything, so it's 2 times 1, 2, plus 2 is 4, and 4 is its own subarray, and 4 gives you 8, right? Because there's this subarray, That's one subarray, gives you 4. There's this subarray, right, from 1, 2 to 1, 4. We've already accounted for that sum in the previous thing, so we don't need to add any additional information, right? And there's 2 of these subarrays where they end in 4, but we've already accounted for that information here, so we just have to add this 1, 4. So that's the beauty of this problem. And with that, let's submit the solution. Oh. How foolish. All right, and with that, that's my best attempt at giving you a solution. It's definitely a very difficult problem because you have a running sum, and you have this monotonically increasing stack, and as you add values, you're basically saying each value that comes before this value represents a subarray, the minimum value in a subarray starting at a value, ending at the value that we're adding, and we do that for each value that we add, and we use a running sum to remove and basically replace previous sums and then adding those total sums. So, I mean, if you have an opportunity, take a look at the solution here. You're going to notice that this is very convoluted, right? I mean, do you notice this is all for one solution because it is no medium problem has a explanation that's this long. You know what I mean? Okay. So this is a very hard problem. So if you didn't get it, don't feel discouraged. All right, everybody, have a good